So we're gonna start. So our second talk of this afternoon presentation is for someone who doesn't need any introduction, but Professor Stéphane Mallat. But for people that don't know him, so I mean, I knew him as a father of wavelets. Reading your books, but from I don't know how many years from you are trying to open the black box of the deep learning machine. So I say that you are coloring the black box, but try to give a new aspect. So thank you for coming. So he's professor in the Collège de France. So it's the highest institute of education in France. So we are really happy to have you here. So thank you for coming.
Thank you very much for this warm welcoming and for the invitation. So, well, it's interesting because the overall workshop is about geometry, but geometry is really a big bag in which we can put almost anything. So I will be looking at geometry from yet a different point of view and insert it into the framework of harmonic analysis, multiscale representation. So this, what I'll be showing is an overview a bit of number of works with collaborators that I'll be mentioning on the way who are there. And the topic will really be at the frontier between physics and image processing. So from the point of view of physics, when you have a physical system at equilibrium, what you would dream to be able to do is from data, from examples, is to learn the physics. In other words, to learn the energy, the interaction. And if the system is at equilibrium, then you know that the probability distribution of the state, so X will always be the data here. This is a standard machine learning notation. So in the case of physics, that would correspond, for example, to a turbulent fluid, or in the case of the cosmic web, density of matter in the universe, and you want to compute the probability distribution, if it is at equilibrium, then you know that it's defined from the energy of the system, which is the Gibbs energy. And the key question is, can you learn this very high dimensional functional, which is the Gibbs energy? And a priori, it's extremely difficult because we are in high dimension. And more specifically, what statistical physics had lots of problem to address is whenever your field has geometrical structures, and in particular in turbulence, it's still totally an open problem to compute the Gibbs energy of such a field. Now, in machine learning, we are having very spectacular results. We now can compute probability distribution whose realizations are, for example, faces or much more complicated even images that you've seen in DALI and with all these software. Now, the question when you look at these beautiful images with neural network, which have been trained on huge data set, is whether the neural network is giving you back an image which somewhere it has memorized from the training set with some kind of interpolation or slight modification, or whether it really learns a probability distribution. And in this case, what does it mean to speak about the probability distribution of faces? The other question is, of course, if it learns a probability distribution, how come, again, it's able to circumvent the curse of dimensionality? In other words, how come is it able to learn such a high dimensional function? So these will be the questions that I'll try to address in this talk with really two parts. The first part corresponds to this question about memorization. Are these neural networks just memorizing from, and think of ChatGPT when it answers you from after being trained on the internet, is it just memorizing or is it really generalizing? And if it generalizes, what kind of prior does it use about the system architecture? And then, as you mentioned, we'll try to open a little bit the black box, which is the neural network, and try to look what is inside. And I'll look particularly at problems which are slightly simpler than phases, at least better posed, which is problems in physics such as turbulence, and try to understand how you can find regularities within this probability distribution. And we'll see that one very strong property that comes out comes from the renormalization group, which is a standard theory of physics, which explains the relation, or which tries to model the relation of physical fields across scales. And I'll try to show in what sense that brings very strong regularity information, including to capture the geometry of the field. So that will be the overall framework. Now, there is a key idea behind all this that we'll be using, which is quite old, to model a probability distribution, is to model it through a transport. So the idea is that if you have a probability distribution, which is here on the left, which can potentially be very complex, what you can try to do is to define a transport which progressively simplifies this probability distribution up to arriving, hopefully, to something very simple, such as a Gaussian distribution. Now, if you can do that, then what you can try to hope to do is then to invert this transport, which, in other words, build a map which goes from this very simple here Gaussian distribution back to the original probability distribution. Now, this strategy is at the heart, for example, of the idea of Markov chains, where you build your probability distribution with conditional probability, which defines the transports. It is at the heart of the renormalization groups, where the transport is across scale, and I'll be explaining that. But it's also at the heart of the most effective algorithm to generate images with neural network, which with this score diffusion model. Although the axis along which the transport is done in each case is different. And in that case, it will be adding noise, which provides a diffusion on the probability distribution. So let me begin with this point of view. So how does these amazing images are produced with these neural networks? So the idea is amazingly simple. You begin with an image, say a face, which is here on the left, and you run a stochastic differential equation, which is called the Ornstein-Uhlenbeck equation, which basically just adds white noise on the image with a slight renormalization. And you get what you see here. Progressively, you have more and more and more noise up to the point that where the noise, which is a Gaussian white noise, totally dominates. So you go from a probability distribution of phase, which is incredibly complicated, to a simple Gaussian probability distribution. So you built a transport of your probability distribution. This is the forward map. Now, this stochastic differential equation can be inverted. That's a standard result for that kind of stochastic differential equation. So you can build an inverse. What does that mean, the inverse? It means that you're going to go from the Gaussian white noise and progressively suppress the noise to go back to the original one. So what is the equation which does that? The equation essentially inverts time. And to invert time, what you are going to have is a term which is going to move the image in the direction of high probability images. This is this term which is called the score. I'm going to explain where it comes from. And if you have, with some miracle, been able to learn this score, then you can learn this invert map. That means that now, if you want to build a new face, you just compute a new Gaussian white noise, easy. You run your equation, and you are going to have a new face, and you are sampling the probability of faces, whatever it means, by just sampling Gaussian white. Good. So the key question in all this, what is really very difficult, is, of course, to estimate the score which is the gradient of the log probability. And the huge surprise was that this can be done with a deep neural network. And that's where I'm going to go in. Okay, so what is the idea, first of all, about this inverse equation? How is the score being computed? To understand that, I'm going to do the link between this notion of score, gradient of the log probability, with this idea of suppressing noise. So that's a denoising problem. So you have a signal, X, your image, to which some noise was added, that is here Z, which is a Gaussian white noise with a variance sigma t squared. And what you would like is to suppress the noise. Suppress the noise means you want to compute an estimator X hat of X, which is going to minimize the error. And here the error I'm going to compute as the mean square error. Now, we know very well what X hat is going to minimize this error. It's the conditional probability of X given the observation xt. So this is two lines to prove, but of course, what is extremely difficult is to compute this conditional probability. Now, there is an old result which dates back to the 1960s, which shows, this is just, again, 3 lines integration by part, that if you want to compute the expectation of X given the observation, in fact, what you just need to do is to take the noisy image and move in the direction of the log probability of the noisy image. In other words, you want to move in the direction of the score. That means that the score is giving you the direction, the optimal direction to move in order to remove noise, which is why in this inverse stochastic equation, you basically iterate on applying the score. So the idea of using a neural network is that the neural network is going to try to optimize the denoising task. And if it does an optimal job, then you know that it's going to compute the score. So that's what is being done. So what you do is you have a neural network with whatever complicated architecture. You put in the input the noisy image, which is here. And what you hope is in the output to get an estimation which is as good as possible of the true image. To do that, you're going to have a training set where you know the original image, and you are going to train the weights in order to minimize the error, which is going to be here, the loss of your neural network. Now, if by miracle the neural network has calculated the optimal estimator, then you know that X hat is related to the optimal estimator through the score. So you can derive the score just by computing the difference between X hat and X and renormalizing. And that's what is being done. Okay, so the question here is, how come it works? And I'm going to show you in what sense it works. Does it really estimate the score, or again, does it do some kind of memorization? And why can it be able to do it? So here are examples, standard example. This is on a database of bedrooms. And these are typical images that are resynthesized from a Gaussian white noise. And you see bedrooms, and these bedrooms don't exist in the original database. Again, does it really learn probability distribution, or is it some kind of patch? And that was essentially the intuition most of us has, and I had at least, is that the image is going to be constructed as some kind of patch of the original image, in which case it means it's essentially memorizing in a smart way. Okay, so that's what we're going to look at, and that's a joint work with Zara Zadokai, Florentin Gut, who was at ENS, Eero Simoncelli, the US. So we want to understand, do we really estimate the score, or do we estimate something which is very far from the true score? Now, in statistics, when you ask such a question, you, of course, always have 2 types of error. you have the variance. And here the variance means, is it going to depend very much on the training database? And in particular, if you are doing some kind of memorization, then that means that the score is going to completely depend upon the training database, or not, in which case it means it really generalized. And the second question is the bias, in other words, the error that you obtain if you have no variance term. Does it really converge to the true probability distribution? Okay, so a comment, what kind of neural network? It's typically UNet that are being used. And I'm showing that because that's going to be important in the second part when I'll be looking at the inside of the network. So you see on the left, you put in the original image. It is downsampled at different scale. And then you have these linear weights and nonlinearities that comes in. And then there is within the neural network, a progressive reconstruction up to the output image. And you have about 7 million parameters in such a network, although the images that we're going to use here are not so big, 80 by 8. Okay, so first question, memorize or generalize? So I'm going to show you an experiment. To test that, we're going to take 2 training sets and see whether with these 2 training sets, the neural networks that has learned, so you have one network that learns from one training set and another network that learns from the second training set, are they producing the same images? Are they learning the same thing? So you can begin with a training set which has only one image, okay? You train your 2 networks with only one image, in other words, very little information. Then you give them the same white noise and you synthesize an image. And one network synthesizes one image, the other network synthesizes an image which is totally different. And these images are in fact just the image that you had provided in the training set. In other words, it just memorized. Okay, now you take you train them on 10 images, which are all different, but which have been randomly taken from the same database. So you have 10 images here, 10 images here, which are different. You train, take a white noise, synthesize, and you see these 2 faces, which are totally different. And if you look in the original database, you realize it just memorized, it just restored an image from the net. 100 image, you repeat the same experiment, same thing, it just memorized. In other words, the image that has been synthesized is an image of the training set. And of course, they are different for the 2 training sets. 1,000 images, same thing. The networks, the 2 networks synthesize an image, 2 images which are different and which are images that existed in the training set. 10,000 images. The 2 images looks now not as good. They are a bit different, but they still resemble very much to an image of the training set with some modification. And that's where you begin to imagine it just used some kind of local patch and so on. 100,000 images, and then boom, something amazing happens. The 2 neural nets synthesize essentially the same image, although they've been trained on 2 different training sets. So they began from the same white noise. That means that they've been learning the same transport up to small r. And if you look at the closest image in the training set 1 or in the training set 2, you see that they are very different. So that means that you've really been learning a transport. You don't have any variance term anymore. And the image that you learned is not some kind of simple interpolation from the training set because they are the same, although the 2 training sets were totally different. Okay, now these are results, again, in the generalization regime. Each time we give a white noise, which is the same to the 2 networks trained on 2 databases, and you see that each time it gives back, it's generated images which are very similar. Sometimes there are slight differences, and look at this one. Here, suddenly there are glasses, the other one doesn't have glasses. It is, and that you can analyze. There is a kind of 1 point bifurcation because there are small errors, and boom, this bifurcation can create an instability. But still, you see that up to these small instabilities, it gives you very close elements. You can do the same thing for very different database. This is a database of bedrooms. Again, you see the same phenomena. One image, the two network will give you back an image from the training set, and therefore which are different. 10, 100, 10,000, 1,000, same thing. And when you arrive to 100,000, the two networks synthesize an image which is the same, which looks like a bedroom, but if you look at it very closely, you realize it's a bit of a strange bedroom. And it is different from any image of the original one, but it has captured a probability distribution whose realized has geometric structures which are very close to what you expect from a bedroom with something that looks like a bed, walls, and so on. Yes, so now we see that it generalizes. So the question now, is it converging to the true probability distribution? What does it mean to converge to the true probability distribution? In our case, we know that this is going to be exact. We have a theorem if the networks computes exactly the score. We also know that we compute exactly the score if we have an optimal mean square estimate. So we can translate this problem of do we compute the right probability distribution into do we compute an optimal denoise? Now, to understand that, I'm going to do a link between, because the topic of denoising is one of the oldest topics in signal processing, okay, since Wiener, so 1940s up to now, there has been many algorithms. Now suddenly you have new algorithms to compute that. One may wonder what's the relation with the old algorithms and what is it really doing and why would it be able to compute an optimal estimate? So what I'm going to show is that what it's doing is in fact not so different from what we are used to do, but in a much better way. So what does, again, CNN, a deep neural network, do? It's computing an estimation of the denoised image from the noising image by adding an estimation of the score. Now, the score is the gradient of the log probability. So in other words, it's a gradient of the energy, or at least of the estimation of the energy. Good. So now I'm going to do a simple observation. The neural network that I'm using has no bias. All the nonlinearities are just relu. So it is locally linear. So the map that it's calculating is a locally linear map. As a result, I can write what it's computing, since it's locally linear at a point x, as being the gradient or the Jacobian of S applied to x. If I insert that into this equation, that allows me to write that the denoised image is relatively to the noisy image. Here you have the identity, and this term is just the Hessian of the calculated energy. So what you're really computing is this operator. Now, this is a Hessian, it's a symmetric operator, so I can diagonalize it. And that's where I'm going to do the relation to standard algorithms. For the one who've been in this field, there is a standard, very effective algorithm that had been developed in the 90s, in particular with wavelets at the time, which consists in doing denoising by taking a vector, decomposing it into a basis where it's sparse, and just keep the large coefficient and set all the small coefficient to 0. It's essentially going to do the same thing. Let's compute the basis which diagonalize this Hessian. Okay, let me write it psi k. This is the identity. So this, I can write it within this basis as just a transformation of the noisy coefficient of xt in the basis, and lambda k is just the eigenvalue of identity minus the Hessian. So what is this doing? Each noisy coefficient, which has inside the true value you would like to get plus the noise, you are going to shrink it. You are going to set it to 0 if the noise is much bigger than the signal, and you are going to set it to 1 if the component of the signal is much bigger to the noise. Now, under what condition this is going to give you an optimal estimator? What you need is that the basis needs to concentrate all the signal energy over few coefficients, which are the very few ones that you are going to keep, and all the rest you are going to set it to 0 and essentially suppress most of the noise energy. So to get an optimal estimator is the same thing here than to learn an adapted basis which defines a sparse representation of the signal. So now we can come back to our problem and look, what is the neural network doing? Is it learning an optimal basis? And we are going to do that in a case where we know the properties of the optimal basis, although it's very non-trivial to compute it. The random process I'm going to look at has realizations, which are images. This is X. And these images are geometric images, which are piecewise regular. On the upper half, it is a C alpha, alpha times continuously differentiable. In the lower part, it's also very regular, but there is a discontinuity along a frontier, but the frontier is itself a regular curve. Now, this was a problem that was studied in the 90s. And in the 90s, a number of people proved, there are a lot of works around that the optimal estimator that you can dream to compute is going to have a mean square error that depends upon the noise with an exponent that essentially depends upon the geometric regularity, in other words, on the Lipschitz exponent alpha. The other thing is, to get this optimal result, you need to compute a basis which is going to compress at ideally these images. And what essentially you need to do is to build a harmonic basis on the upper half and on the lower half of the image, essentially a Fourier basis which is adapted to the frontier on the upper and lower half. Okay, question, will CNN do that? And the answer is yes. When you you train your CNN with that kind of images, if you compute the mapping that the CNN computes, you compute the Hessian, you look at the basis which diagonalize the Hessian, what it gives you, the eigenvectors are essentially Fourier basis over the upper half and lower half, so that it doesn't mix the two regions. It compresses it ideally, and you get the optimal slope. In other words, in this case, we can verify that it does do the right job, which is quite impressive because we give it no information. Now, if you begin with a much more complex problem, such as a face, this is your clean face, the noisy face denoised. These are the eigenvectors of the Hessian. And you see, so each image here is one vector. And what you observe is that it oscillates along the geometry. And why is that very useful? Because essentially, what are the regularities? The image is regular when you have an edge, when you move in that direction. And it oscillates in that direction, which allows to compress the image. And it does, so it does something which is indeed very reasonable. Now, the question is, why? How come it's able to compute that kind of? Because this is indeed quite impressive. We can't dismiss it anymore, say, well, this is just because it has a lot of memory, blah, 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 memorized. It does really compute the appropriate operators. So we see that it generalizes it, but if you have enough training samples, don't forget, you need 100,000 images for images 80 by 80. So you need a lot of data. The generalization depends upon the size of the neural network, which is not very surprising. There's all kind of studies now on this. Now, the real difficult and interesting question is how come it can learn such functionals of such high dimension? And there has been a lot of very nice presentation on issues of equivariance and invariance over geometrical groups in the workshop. One comment is that imposing invariance over small geometrical group is not going to kill you the curse of dimensionality, because if you build an invariant to a group of dimensions 2, 3, 4, where you are doing a quotient of your space by base of dimension 2, 3, 4, you are basically reducing the dimension d by 3 or 4. That doesn't solve your problem. You were in dimension 1 million, you go to 1 million minus 3, you are still in very high dimension. So invariance to small groups is not enough here. And if you look at the network, you see this multiscale structure in the UNet. So that will be the guide. We're going to try to understand in what sense this multiscale structure can allow us to understand it. Two questions. The first one that we'll be asking is how come we can indeed grab this geometry? And the second question, which is a kind of graal for in physics, is can we learn turbulence? Can we learn probability distribution of turbulence? Okay, so there I'm going to change field and go to physics. And this amazing idea that is the renormalization group that appeared in the early 1970s with Kadanoff and Wilson that gave Nobel Prize to Wilson. And the idea is the following. If you have a field that is known so if you know your probability distribution P, and you have a sample of your field at very fine scale, if you want to understand the property of your probability distribution, one thing you can do is to progressively lower the resolution of the field. So look at the evolution of the probability distribution when you average the field and subsample. So now you have a field at coarser scale and even coarser scale, and you are going to have a transport of your probability distribution across scale, because this probability distribution is, of course, different than. Now, if you go at very large scale, you end up over a very small field. So now this is going to be simple, not only simple, but this may just be Gaussian, because you've been averaging over such large domain. If you have some independence far away, that's going to converge to a Gaussian process. Not always true if you are at a critical point, but often true. Okay, so the idea is to look at this evolution. What we're going to do is, and the whole physics analysis was in that hour. We're going to go in the reverse direction, and that's the work with Giulio Biroli, Étienne Lempereur, Thierry Marchand, Jacques Zerwa. How do you go that way? Well, you are basically inverting the transport, okay? So you need to go from coarse scale to a finer scale, from a finer scale to a finer scale. That's going to go by computing. What you need is to compute the probability distribution at the fine scale from the probability distribution at the coarse scale. And this is just given by the conditional probability of the fine scale image given the low scale image. The question is, can we compute this? Now, the key idea which was behind the renormalization group is in fact that in physics, these kind of conditional probability are not singular, even if the original probability distribution is singular, in particular, if you renormalize them. So we know that these objects are a priori simpler than the original probability distribution. The other thing that we're going to do is, where that's are going to come in, we are going to represent these conditional probability distribution in a wavelet basis. So why is that? What I'm interested is taking an image of fine scale, reducing its resolution, But when you reduce the resolution, you are losing information. What information are you losing? The high frequencies. Now you can represent the information that you've lost in a Fourier basis or in a wavelet basis. Why am I going to do it in a wavelet basis? Because we're going to see that local structures play a crucial role. That means that I'm going to use a basis which is built with local waves. So a wavelet basis is like a Fourier basis, but it's a local sine wave, which is rotated here in three different directions. And if you dilate it and translate it, you can obtain an orthogonal basis. So what that means is that this image can be decomposed into its projection in a coarser scale and the wavelet coefficients, which you see here as images. These images, whenever you see a point which is gray, it means the coefficient is 0. White, positive, black, negative. You see the large coefficients are along the contours, as you can expect. So what is this conditional probability distribution? Well, xj minus 1 given xj, it's the same thing than computing the wavelet coefficient given the low frequencies. Now, the low frequencies, I can sub-decompose it itself into wavelet coefficient. So what you see is that this is really about understanding the dependencies of wavelet coefficient across them. They're nonlinear dependencies. Can we capture that? And if we can capture that, can it restore the geometry of the random process? So that's the question. And what we're going to try to do is to build the simplest type of probability distribution model. In other words, an exponential model. So it's going to have a linear dependency upon the parameters. And of course, the question is, what is these moment generating functions that you need to plug here to be able to build the model? Okay, so the global idea is you essentially factorize your probability distribution as being a very coarse scale probability distribution, which may be just Gaussian, and then all the conditional probability distribution that you model. And now, if you want to create a new sample, you first sample at a very coarse scale, which is low dimensional, and then you compute a sample of the wavelet coefficients by sampling the conditional probability distribution given the low frequency. You reconstruct the next scale. You sample the wavelet coefficient given the low frequency. I'm sorry, the low frequency is here. Up, you reconstruct, and then you sample the conditional probability distribution, and so on. Essentially, it looks a bit like a unit pipe. You go down, and then you reconstruct progressively by sampling the conditional probability distribution. Just to give you an intuition what the transform is doing, if you have an image like here, whose Fourier transform is supported on a square, when you do a first one-scale wavelet transform, you essentially divide the Fourier domain in two domains, the low frequencies in red, which corresponds to this image, and the three images which extract the contour, which corresponds to the high frequencies in different directions. And then when you continue, you split again the Fourier domain, you split it again, you split it again. So it's a recursive kind of splitting of the Fourier domain, but which is local in space. Good. So now the problem is to compute this conditional probability distribution. Let's take a complex images such as this boat, which has all kinds of geometry. These will be the wavelet images at different orientation and different scale. What you see immediately is that the geometry propagates across scale. You still see a boat over all these images. So obviously, they are very dependent. But if you try to compute the correlation, the linear correlation between these images, you will get 0. Why? Because you have a phase which oscillates. These images, as I showed, they belong to different frequency bands. So when you have frequency which oscillates at different speed, so when you do the correlation, you essentially get 0 correlation. So the question is how to capture the dependencies across scale. And that's where we're going to see the need for a nonlinearity, which of course appears everywhere in these neural networks. Suppose you do something naive. You know that the phase is responsible for killing the correlation. So let's kill the phase. You take a modulus. If you take the modulus, in other words, you compute the amplitude of the wavelet coefficient, you get a kind of edge detection. You see the large coefficient, which are shown in black, correspond essentially to the edges calculated in different direction. And here, these images are very similar. So if you compute the correlation of these images, you are going to have a very strong correlation. The problem is that the correlation is going to be very long range because the regularity of the geometry means that there are some very strong correlation from points which are very far away. And that's the difficulty of capturing geometry in a random process. It's because it creates very long range dependencies. And if you want to estimate it, you are going to end up with models with huge amount of parameters. What you need to do is find a representation where these long range dependencies are going to become local. And that's the sense of all what we're going to do here. Relocalize the dependency resulting from the geometrical regularity. Let's take a simple example, a circle. This is the modulus of the wavelet coefficients in different scales. So you essentially see that it computes the contours in different direction and at different scale. Okay, now let me do a bit like the wavelet a neural network. I've applied my nonlinearity, and then I reapply a linear operator. But the linear operator I'm going to apply, I would like to sparsify the image. But this image, if you look at it, it's now very regular if you move in the vertical direction. Because the first wavelet has selected edges in one direction. So if the geometry is regular, if you move in the perpendicular direction, everything is going to be regular. So if you now compute these wavelet coefficients and you look at them, essentially they are all straight. You are showing the geometrical regularity here by the fact that you have these second order wavelet coefficients, the next layer, which are zero. The first layer, the standard wavelet coefficients, are not small because you have a discontinuity. But because the discontinuity propagates along a regular curve, you are able to kill these coefficients with the second layer coefficient. What if you have a corner? This is a simple example. So this is a square. These are the edges in different directions. And now if you take the wavelet coefficients and you filter them in the perpendicular direction, so you look at the high frequency in this direction, locally, it's going to set all coefficients to zero besides the corner, because at the corner you have a discontinuity in this direction, and you see appearing these sparse images. So again, you see the piecewise regularity of the geometry through this second order coefficient. And that's the only theorem of the talk. You can indeed prove it by supposing that you have an image which is piecewise C2 and computing this coefficient and showing that the decay of the wavelet coefficient are essentially depending upon the geometrical regularity. If you look deeper, in other words, not just with a linear map, but with a succession of linear maps. Okay, let me finish by coming back to my problem. My problem is to build a stochastic model. To build this stochastic model, I build a model of the wavelet coefficients. And more precisely, what I need is to build a model of just the conditional probability of the fine scale coefficient given the coarser scale coefficient. And I would like to compute it with some linear operator, linear exponential model. Okay, what I saw is that some of the key information here is of course going to be the wavelet coefficient, but also the modulus of the wavelet coefficient, which have been refiltered by a second layer wavelet. That's we had been studying for a number of years called the scattering transform. So you alternate wavelet transform modulus, wavelet transform. And now I'm going to build the simplest possible model. I'm going to look at the covariance of these coefficients. So now I'm going to look at the dependencies of wavelet coefficient across scale. But these correlations are not going to be zero anymore because I've taken the modulus. I killed the original phase. So I'm going to look at the covariance matrix of these scattering coefficients. And so the models that I'm building is just a model which is defined by these parameters, which are in fact the interaction coefficient between the wavelet or the scattering coefficient at one scale and at the other scale. Now, what I said is that the goal is to have a small model. To have a small model, you need to take your very long-range dependencies and make it local. I'm going to impose furthermore that the matrices here, the interaction matrices, the correlation, I only keep the local correlation. In other words, between coefficients which have the same position, but at different scales. So I really look at the interaction across scale. If you have an image of size D, normally a high-dimensional model is going to have a probability distribution model is going to have a number of parameters which grow exponentially with D. If you use a simple covariance model, it's going to be T squared. Here, because we kill all long-range interactions, the number of coefficients is small, is log D cubed. And I'm going to show you results in the case of physics. So these are images of different physical fields. Okay, you have D is about 50,000. So these are images of 256 by 256. We learn from the database and we sample. And here are the samples of the probability distribution that are calculated from the scattering coefficient. And what you can see is that you are restoring the geometry. The regularity of this field, the geometrical regularity, this looks very similar to the regularity of the region. So then the question is it just that it looks good, or are the statistical properties of these two distributions very good? But what you can do to test whether this random process that corresponds to the model is close to this one is to look at higher order models, which we did. We looked at spectrum, the bispectrum, which is third order and fourth order terms, and you get a very close match, at least up to the order 4. One point is the model here has only 500 parameters, as opposed to the UNet, which had 7 million parameters. So that's an indication that doing some math can be useful, although we are far from mastering the math. But the consequence of that is that you can learn with much fewer examples. And this is a key problem. I showed in the case of faces, you need about 100,000 faces to generalize on 50 by 80 by 80. These are much bigger images. And you typically don't have so many numerical experiments or observation in physics. So that's an important issue. This is another example on a much simpler image, just a circle. The question is, by doing this just interaction across scale, so at no point do we have a model of the contour. The model of the contours goes indirectly through the interaction of the scattering coefficient across scale. Can we reproduce it? And the answer is yes. These are samples of the scattering model. We have no proof of one. But this is a somewhat well-posed problem. Why? We know in what direction that this kind of model is going to create sparsity in the representation. But the fact that this sparsity is enough to really just restore circles was a surprise. We clearly can't restore faces. Faces are much too complex to do that with simple models such as these scattering models. Okay, so let me conclude on that. the first conclusion is that we should take seriously these neural network stochastic models. They are really building impressive models of probability distribution. This is not just about storing images and restoring some kind of distorted images. And what is absolutely key in the construction of this probability distribution is what the community called the inductive bias. In other words, the architecture of the neural network is imposing a very strong regularization on the calculation of the probability distribution, which is not going to always work, but which is working on a very large class of problems. And there is this relation with these geometrically adapted bases, which is one possible tool to analyze the math. And this is a work with Zara Zadokai, Florentin Gut, and Eros Simonche. The second part is really about the physics. And this is a very open problem in physics. If you look at the literature in physics concerning the renormalization group, it has beautiful application on easing, 2D, 3D, where you can observe critical phenomena. But whenever you move to much more complex phenomena, such as turbulence, nobody up to now has been able to really compute a renormalization group decomposition of turbulent field. This is only numerical, but there is clearly now some very beautiful problem to understand. Of course, the Graal would be to do the relation with Navier-Stokes, but we are very far from that. But let's just say that, so that's a work that was done with, so Julio Bironi is a physicist, and I said Thierry Marchand and Jacques Zawa. We've been building some models of physics with Xiao Cheng, and we are now trying to understand a bit more the math which is behind. How come we can stabilize these calculations? But again, we are very, very far from the physics equation. And that would be the understanding what sense the approximation we built is related to the structure of the equation. So I will be finishing on that. Thanks very much.
Thank you, Stéphane, for being on time. So we have time for questions. Some question. So okay.
Yeah.
Thank you, Stéphane, for your talk. For turbulences, so we know we Interest, we collaborate with Onera, so we are able to generate with physics some model of turbulences with eddy dissipation rates. So it could be interesting to compare generation of images of turbulences from physics and from your technology. What is important in turbulences is also to look at the time evolution. So are you able to also generate sequence of images of turbulences with coherent physical
Okay.
and
So
to capture the dissipation of the phenomena?
Thanks. So that's an important question. I'm not doing it, but there is a huge community now which are doing that. Huge community, because as we're saying, the application are very important. So they are building models of turbulences with very large network, including transformers. There is many. The state of the art moves incredibly quickly. One application of that kind of thing is meteorology. And as you probably know, 2 years ago, these things were working a bit, but really not as good as. 1 year ago, there was beginning to have results. Now you have systems which are doing predictions on scale of 3 days up to a week, which are better than Météo France on standard databases. So the field is moving very quickly. That the fact that they can predict meteorology means that there is some form of generalization. Now, for turbulence, for example, in our geometry, like for airplanes and things like that, frankly, I don't know. The problem, and it's exactly what you're saying, is that you can build beautiful images which are totally wrong at interface. And when you're wrong at interface, you lose absolutely everything. And the question also is very much related to this question of generalization. Again, it's simple to build good-looking images, but are you just reproducing the image of your database, or are you really generalizing? Do you have enough entropy to really get the range of possible? So this is a moving domain, but I imagine in Thales there must be people working on that because, or at least if it's not, they should, because this is, I think the way it should be seen is not as replacement of numerical analysis. Numerical analysis can get you very precise, if well done, result at precision 10 to the minus 5, 10 to the minus 8. But these can generate very quickly things which are somewhat reasonable, which allows to have very fast design. That's what they do now in automotive industry. You want to design the shape of a car, you need to have a vague idea of what is going to be the aerodynamics. You can do a quick simulation. So it's a moving field.
In fact, there is different community working on this topic. For example, you have a spin-off of EPFL, which is called Neural Concept, which work with industry, more purely neural network oriented. You have Adagos in Toulouse with topological gradients. So the idea to have the smaller neural network to be able to extrapolate some cases. In Thales, we try to mix with model because for a pure deep learning approach, we consider that the analytical model is bullshit, and you will learn Maxwell equation, Navier-Stokes equation with learning. But we have this equation. So this equation offers good approximation of the problem. And some topic like physics-informed neural network track to mix between the model and the data. Also, because in industry we have less data, and it costs a lot to have this data and to make some tests. And so, what is your position between the balancing between model and pure data analysis?
I mean, it makes sense to mix with models. It depends the amount of data you have. That's exactly what happened with meteorology. They first tried by mixing the two, and then you had guys who got huge databases, and they showed they were getting better than the mixing. And so each time it evolved. But I should say there is, I think, two different, basically, kind of problem. There is, on one hand, getting the best prediction, and here the numerical results are very impressive. On the other hand, there is the other question, which is understanding what is behind all this. And this is important for physics because at the end of the day, for physics, you want to understand physical properties. You don't just want to create, and there are much less people working on that. And so I can only invite PhD students who are interested in working on this kind of case, because the crowd in machine learning is terrifying. Any topic is studied simultaneously by thousands of people. You don't know where in China is on. The good thing about the interface of math with math is you have much less people working. So that's one reason why you may be interested in this.
You have any questions? I can actually, just to come back to the first part. So your interpretation is in a subfamily of models because you are not using bias. But for practitioners, we know that normalization with bias is really important to convert in a good model. So do you have comments about that?
Sorry.
Your model, you are not using bias in your model.
No, we are not using that.
But from a practical point of view, we know that when you add bias and normalization layer, the conversion of the models are faster.
Yeah, it can indeed improve. Again, eliminating the bias was a way to simplify the math and allows to have an analysis. But the cost in terms of performance is small. the bias improves you a little bit, but not so much. So in that sense, it's not, I mean, when I mean bias is when you have a rectifier, you can apply the rectifier directly on the coefficient coming from the previous layer, or you can apply it with a bias, so by adding a constant that is being known. And these biases don't, if you train without bias, if the architectures are appropriate, you still get about the same time. Maybe not as fast, but so in other words, the bias are not fundamental in these UNet architectures.
No questions? You are eager to go to the coffee break? Okay, let's our speaker.
Thanks.
So we move to the coffee break and we take some minutes for a photo group. Bonjour, comment ça va?
Ça fait 22 ans.